Okay, now we are going to go ahead and work through the note sheet that goes along with the lab. So I filled some things in already. We are obviously working with a cupcake, and we looked at in my instructional video that when we sliced into the cupcake and we then cut the half into 2/4, we saw that the shape of the cross section, the two-dimensional cross section, was a trapezoid, and that is very, very important in order to find the volume of this cupcake. Okay, so when I took my measurements, and I said them in my video, I had the shorter radius of my trapezoid was 2.3, and that ran parallel to the longer radius, which is the top of the cupcake essentially, which is 2.8. And then the height of the cupcake from top to bottom that connected those two parallel sides for me was 4.0. Now it would be cool if you got different measurements, round them to the nearest tenth to make the mathematics as easy as we can. Okay, but now what we are asked to do is we are asked to sketch, it should say our food, sketch your food, sorry, there is a typo right here, sketch your food, such that the axis of revolution is the toothpick. Okay, so the toothpick is the x-axis. Okay, here is our toothpick that I'm drawing in purple. So we can picture, okay, that the, I'm going to actually put the top of the cupcake over here, and I'm going to put the bottom of the cupcake on the y-axis from when we made the slice. Okay, so what is this portion going to be right here? This is actually going to be the height of our cupcake. So if we go ahead and put together our measurements, okay, remember the top is the larger radius, the longer radius. So I'm going to go ahead and graph 2.8, or sorry, let's start with the shorter radius. Okay, so I'm going to go ahead and graph the bottom of my cupcake, which is the smaller portion, at 2.3. Okay, and then I'm going to go ahead and graph the top, but I need to think about where's the top going to be. It's going to be 4 centimeters away from where the bottom is sitting. So we're going to go over to 4, and I'm going to go up to 2.8. Okay, and we can label these points. This point right here is 4, 2.8, everything measured in centimeters. And then the point on the y-axis is 0, 2.3. Now hopefully you can start to see that trapezoidal shape taking place. Okay, I think I can actually draw a line between the two. Okay, so there is kind of that V shape that occurs on the cupcake. And then I can think about, okay, here is the, whoops, undo. Okay, and then I have my top of my cupcake here, and I have the bottom of my cupcake here. So there's that trapezoidal. You can picture kind of the icing that was inside here. There is the cross section of our cupcake. Okay, so how are we going to find the equation for the top function? Okay, it is a linear function. In other words, what is going to define basically the radius as we go through the entire cupcake, okay, because all of these eventually are going to be radii of a circle. Okay, so we are essentially looking at how am I going to find the heights of these radii, these different radii that I just drew in. Well, we need to find the function of that's formed by that red line. Okay, so I'm going to use my 2 points, and I'm going to find the slope because that is linear. That's why we're starting with a nice trapezoid, okay? So my slope, I'm going to go ahead and take 2.8 minus 2.3 over 4 minus 0, and when I do the calculation, I end up getting 1/8. So my numbers worked out nicely. If yours are decimals, go ahead and round to the nearest thousandth, 3 decimal places. Okay, so then from there, I am going to just take advantage of my y-intercept and see that my line is going to be y equals 1/8 x and then plus 2.3. Okay, so that alone is not going to necessarily define the height, but then when we see that the bottom equation, which I can go ahead and put blue over, what is the equation for this line? Well, it's the x-axis, so y equals 0, which is very nice, okay, because then from that point, we can just say that if our toothpick, remember, the blue now becomes the toothpick, is going through the x-axis, then we can go ahead and just utilize our top function, our linear top function, to define the radius of every circle that we are about to consider, which I started to show you with cutting my second cupcake in the video. Okay, so hang with me here. So now when we go to the back, okay, it says what shape was the cross section when we sliced it perpendicular to the toothpick. It was a circle. Okay, and then on part C, it says that in calc, we are going to refer to circles with no, sorry, lots of typos here, with no holes in the center. Those are going to be called discs, okay? But then when we look at a circle that has a hole in the center, and that was in the video when I said imagine the icing being taken out, those are going to be called washers, okay? But for today's lesson, because there was icing, we're imagining the cupcake to be completely solid, okay? We are working with discs. Okay, so now that we put together that we are using multiple circles to form our cupcake, which is at the end of video 2 where I kind of shoved all the circles together and it made a smushed looking cupcake, okay, we now know a formula, we should all know a formula for our cross section of a circle. Okay, what is that cross section formula? The area of a circle is pi r squared. All right, but then the question is, are all radii of our circles the same length? And I kind of showed you 2 circles side by side, and if you just think of the bottom of the cupcake versus the top of the cupcake, are they going to be the same length? No. That is why our trapezoid kind of shape was created, because we start at the bottom of the cupcake with a relatively small circle, and then we kind of got bigger and bigger and bigger until we got to, okay, the top of the cupcake. So what shape did that form? That formed a trapezoid. So you can see that the discs are used to come together over a span or a change in x to form kind of the cross section that we're then going to think about in terms of our rotation. So, what determines the length of the radius? Well, I'm going to choose red because that's what I use. It is that linear function from page 1. What was our linear function? It was y equals, for me, 1/8 x plus 2.3. Yours might be slightly different. And we also need to specify that we chose to put that axis of revolution at the x-axis. Okay, so now here is kind of where the big calculus idea is going to come into play. Okay, we want to go ahead and think about integrating the height of the function integrating the height of a function gave us area. Okay, so we know that from chapter 4. But then if we think about taking a step further, this is kind of like when we talked about position, velocity, and acceleration with derivatives. Okay, well now we're thinking about function, area, and then volume. So the key idea of chapter 7 is that when we integrate area, that gets us to volume. Okay, so we want to go ahead and find the volume, and it says write an integral using the area of the cross sections, okay, and substitute r with the function that defines the radius. Okay, so if we go back up to our paper now, okay, this red function, you might want to go ahead and note, is this function defines the radius of each disk. Okay, so now we're going to actually make kind of like a three-dimensional representation. So if we think about in purple, okay, the purple is already our radius, so that is going to kind of mirror image below that toothpick, that axis of revolution, and I'm going to make it about kind of the same length, okay? And we can go ahead and see that here is going to be a disk that creates and is used in our cupcake. Okay, so a lot of times when we do these problems, we're going to draw in those circles of the top and the bottom and kind of leave the middle alone. Okay, so I want to go ahead and draw a mirror image of 2.3 on the x-axis. Then I want to go over to 4 and I want to draw the image of 2.8. And then I want to mirror image the red line that connects the two. And then I can picture kind of drawing in the disk with a radius of 2.8. And I want to picture drawing in a disk with a radius of 2.3. Okay, and then you can kind of see the shape take place. So this is like a cupcake on its side. I'm holding the ends of the toothpick, kind of like you may have seen me do in the video. So the key idea is that we are trying to find the area of each disc involved, of each circle, and then we are going to integrate, okay, along the interval from 0 to 4, which is defined by our height. Okay, but the radii are changing. So we have to know, how are we going to find the height of each radius? Well, the height is going to occur on this function, okay, which we saw it was a trapezoid, but then it led us to look at kind of the idea of this linear model that is going to give us the radius at each point between 0 and 4. Okay. So now if we scroll down, we want to create an integral to find, again, the volume of the cupcake. So the hint is we want to integrate, okay, and we're going to integrate area of the disk, which is a circle. So area equals pi r squared, and in this case we would be integrating with respect to the radius because the radius is changing. Okay, so this is what the variable looks at, the variable that would be changing on our span. Okay, now we need to be careful of our upper and lower limits, and that is given by the height or the amount of the toothpick that is covered by the cupcake. So we're going from 0 to 4. It's always good to take advantage of the origin and use your axes. Okay, but we need to do some substitution, and we need to take advantage of the function that defines our radius. So we're not going to integrate pi r squared. We are going to look at integrating pi times our function, which mine was 1/8 x plus 2.3. So I've replaced that so now it's dx, and actually this is when I should add in my limits of integration because they're written in terms of x. So I should probably go back and go ahead and erase these until my variable is x, and then I can look off the x-axis. Okay, now this pi is constant because every circle is going to include that constant. So now when we evaluate the antiderivative on part B, we are going to pull the pi out front, 0 to 4. And then I am going to look at 1/8 x plus 2.3 dx. Okay, and then I can go through all the math, but you guys also can use the functions on your calculator. So when I do this integral from 0 to 4, okay, I end up getting that the volume of my cupcake is 81.975 centimeters cubed. Done. Okay, so we use the idea that repeating circles and smushing those together from 0 to 4 is going to give us the volume. And this is called the disk method, what we just did. And we're going to use the disk method over and over and over again these next few days. Okay, so for homework, what I would like you to do before you submit these notes or proof that you went through the lab, I would like you to consider questions 7 and 8, just kind of pulling it all together and thinking about how you can check to make sure that your answer is kind of somewhat accurate and not completely off track. Just one key thing is, remember, volume of a rectangular solid is going to be length times width times height. Okay, so that's all I'm going to say there. So go ahead and finish these 2 questions, think about what we did today, and then we will take formal notes on this tomorrow. But again, why not put in something a little hands-on, even if we're at home. Hope you enjoyed the food lab. Now you can go ahead and indulge in that cupcake, and that's all I've got for you today. Great job.